Welcome to the session, continuation of chapter 4. Under this, I am discussing 4.1, that is PMMC. In that PMMC, one more concept is, we know that to convert PMMC as ammeter, we are connecting shunt resistance. To convert PMMC as a voltmeter, we are connecting series resistance. Then what the properties of shunt resistance and what the properties of series resistance are multipliers that I want to discuss. Okay. Listen please. One is properties of shunt resistance. Shunt resistance. Whatever the shunt resistance we are using, which properties it satisfies. One property is it must be less temperature coefficient or less sensitive to temperature. Less temperature coefficient or less sensitive to temperature. The material which is having less temperature coefficient, that is less sensitive to temperature or less sensitive to temperature. Sensitive to temperature. This is one of the properties of shunt resistance. Another property is whatever the shunt resistance, whatever the material used for the shunt resistance, it must be, its resistance should not vary with respect to time. Its resistance should not vary with respect to time. With respect to time. Yes, means it must be linear resistance. It must carry the current without excessive rise of temperature. Carry the current. Yes, carry the current without excessive rise of temperature. Without excessive rise of temperature. It should produce less thermal EMF. It must produce less thermal EMF. What is the thermal EMF? I will explain. Less thermal EMF. The properties which satisfy all these properties, that material is more preferable to manufacture the shunt resistance. That is properties of shunt. What are the properties of series resistance or multipliers? Properties of series resistance or multipliers. It's also called multiplier resistance. Multipliers. It is also less temperature coefficient, that is less sensitive to temperature. Less sensitive to temperature. Next, resistance should not vary with respect to time. Resistance should not vary with respect to time. Carry the current without excessive rise of temperature. Carry the current without excessive rise of temperature. excessive rise of temperature. Another property is it should be non-inductively wound. It should be non-inductively wound for AC meters. Okay, these are the properties of shunt and series multipliers we are using. Okay, but point to remember, to satisfy all these properties, in general, RSH and RSC is made with either manganese or constantan. That is, to satisfy these properties, RSH and RSC is made with either manganese or constant. Either manganese or constant. Either manganese or constant. But point to remember, manganese or constant and both are properties are having nearly zero temperature coefficient. This is the property. Nearly zero temperature. That is very less temperature coefficient materials. Nearly zero temperature coefficient. But both are brittle in nature. Both are brittle in nature. But point to remember, manganese is more preferable for DC. Manganese is more preferable for DC instrument because it produces less thermal EMF with DC. Less thermal EMF with DC. In general, if it is asked for DC means your answer is manganese. But constantan is more preferable for AC. More preferable for AC because it produces less thermal EMF with AC. Less thermal EMF with AC. Like this, if AC and DC is asked means, then according to this we can select. But as compared to constantan, manganese is more preferable. Generally, as compared to, because manganese is less cost as compared to constantan. As compared to constantan, if it is asked AC or DC means like this we can select. But generally asked, then as compared to constantan, manganese is more preferable. Manganese is more preferable. Okay. Okay, this is about the selection of what exactly shunt and series. This is the construction of shunt resistance. This is the construction of series resistance or multiplier resistances. Okay. But one point to remember, up to 500 volts only, these multiplier resistances are made within the instrument. But greater than 500 volts, these multiplier resistances are made outside the instrument. We can make special mounting of this arrangement. Because above 500 volts also, if you use this multiplier resistance within the instrument means, then because of large temperature rise, meter maybe. That's why to make the temperature limit, then to limit the temperature rise, then it's made outside. Here also, for less than 200 amperes only, we can use this shunt resistance within the instrument. But greater than 200 amperes, we can go for outside the instrument to limit the rise of temperature. Okay, that point you remember. Here, the instruments, the material which produces the less thermal EMF, that is more favorable. Mainly that point is considered in the ammeters, in the shunt resistances only. But no need of any, we don't have any this concept in the case of multiplier resistances. Okay, that's why in the selection of shunt resistance, but for multiplier resistance we can use either manganese or constant, but more favorable is manganese, no doubt at all. But in the selection of a material for the shunt resistance, the material which produces the less thermal EMF, that is more favorable. Okay, then what is the thermal EMF? Thermal EMF. What do you mean by thermal EMF? Listen please. Let us consider ammeter, PMMC ammeter. Okay, this is shunt resistance. This is the shunt resistance. And this is PMMC meter moment. And this is the meter resistance. This is the meter resistance. Okay. Then listen please. This is generally it is made with which material? Manganese material. This is made with manganese, and this is the copper resistance. This is the copper wire. It just like this is manganese. One material is manganese. Another material is constant. This is manganese. Sorry, another one is copper. It just like two dissimilar metals are joined together. Na? If the two dissimilar metals are joined together, because of temperature difference between the two junctions, an EMF is induced. That EMF is called thermal EMF. Because if this EMF is more, if this EMF is high, then because of this EMF, the pointer deflection will be changes, then it gives the wrong readings. Okay, this that's why the material which produces the less thermal EMF, that material is more favorable. Okay, this is according to Seebeck effect. This concept is according to Seebeck effect. I think we studied what is the Seebeck effect, Peltier effect, Thomson effect, all this. Then according to Seebeck effect, what the thermal EMF means? According to Seebeck effect, you note down this. According to Seebeck effect, if the two dissimilar metals are joined together, two dissimilar metals are joined together, because of temperature difference between the two junctions, because of temperature difference between two junctions, difference, yes, between two junctions, an EMF is induced. Yes, an EMF is induced. Yes, it is called thermal EMF. It is called thermal EMF, and it is in the range of microvolts. Yes, in the range of microvolts. Okay, this what exactly? Thermal EMF. It is in the range of microvolts. Okay, but point to remember, thermocouple works on the principle of Seebeck effect. Important point. Thermocouple, yes, works on the principle of Seebeck effect. Works on the principle of Seebeck effect. Okay, this is the what exactly thermal EMF. That's the reason why the material which produces less thermal EMF, that material is preferable. But you have the one doubt here, sir. Because of RSH is made with manganese material only, thermal EMF is produced. That's the reason why, because of two dissimilar metals, it gives the wrong reading. Why you can made with manganese? Directly we can use copper also here. Copper shunts we can use. This is copper and this is copper. Similar materials, no EMF, no error. That is meaningless. Thermal EMF effect is very less. That is negligible. It is in microvolts. But if you use shunt is made with copper material, copper is more sensitive to temperature, then it gives the high temperature errors. That is one problem. Then if the copper shunts are used, if you use copper shunts, then what is the size of the meter will be increased. That is, weight of the meter is increases. Size is also increased. That is the problem. That's why if the shunts are made with copper material, size and weight of the meter will be increases, and temperature errors also increases. That note also you remember. That's why we never use, in order to reduce the thermal EMF, in order to eliminate that thermal EMF, I will use shunt is also with copper material, means that is meaningless. Okay, microvolts means it is negligible effect, no doubt at all. But if it is made with copper material, it gives a more temperature errors. If shunts are made with, multipliers made with, if shunt and multipliers are made with copper, temperature errors are increases, and weight of the meter is also increases. Hence, we never made with shunt and series resistances with copper. We can use either manganese or constant only. If you use copper material, these properties will not satisfy. Then it gives the more errors. That's why shunt and series multipliers must be made with either manganese or constant. But generally manganese is more preferable. You specially is asked for AC, means you take manganese. For DC, you take constant. This AC and DC concept mainly you consider in the case of ammeter. No need in the case of voltmeter. Because there is no any joining of two dissimilar metals. There is no closed path like this. Okay, in the case of voltmeter, because totally it is a series branch. But thermal EMF effect is not the case in the case of voltmeter. Mainly that you consider only in the case of ammeter. Clear? Understand? Okay, this about what exactly properties of construction of shunt resistance and series resistance. Then one more theory concept with respect to PMMC that is also important. Put siding swamping resistance. What is the purpose of using swamping resistance? So over? Clear? Okay, concentrate. Swamping resistance. Yes. outside swamping resistance. The point to remember what the swamping resistance means, denoted by RSW. Yes. Manganese plus copper. Manganese plus copper. 20:1 ratio or 30:1 ratio is called swamping resistance. If we select manganese plus copper 20:1 ratio or 30:1 ratio. Swamping resistance means it is not a separate resistance. It is also one of the manganese resistance. But why the name is given as a swamping resistance means the purpose of using swamping resistance is it is used to reduce the temperature errors in ammeters. Mainly swamping resistance is required only in ammeters, but no need of any swamping resistance in the case of voltmeter. The reason I will explain. Okay, that is, it is used to reduce temperature errors in ammeters. It is used to reduce temperature errors in ammeters. Temperature errors in ammeters. That is the purpose of using swamping resistance. One more point to remember, swamping resistance is connected in series with meter. Swamping resistance is connected. Resistance is connected in series with meter. In series with meter. Next, in general, swamping resistance equal to 20 to 30 times of meter resistance or coil resistance times of coil resistance or meter resistance. 20 to 30 times of coil resistance. This much of swamping resistance we can select. Then let us consider a PMMC ammeter. Let us consider a PMMC ammeter without swamping resistance. Let this is the shunt resistance RSH. Okay, this is meter resistance is RM, and this is PMMC meter moment. Okay, PMMC meter moment. Then this is PMMC ammeter. This current is I. This is ISH. This is IM. Then in this case, what is RSH equal to? RM by M minus 1. This formula you know. Then to reduce the temperature error, we are using swamping resistance. This is RSH, let this is RSH dash. With the swamping resistance, the value will be changes, design value. This RM is the meter resistance. Yes, this is PMMC meter moment. Then this is RSW. Swamping resistance is always connected in series with meter. Then always meter current is IM. Okay. Then from this, how we can write RSH dash equal to, that is RM plus RSW by M minus 1. With swamping resistance, how to calculate shunt resistance, where RSH dash is greater than RSH. Okay. This is without swamping resistance. This is with swamping resistance. The swamping resistance is connected in series with meter. Now the question is, sir, how this swamping resistance will reduce the temperature errors? Here I am giving theoretical proof. For example, if temperature is changes, this I am giving variable symbol like this. If temperature is changes, then what the meter resistance is also changes. then whatever the meter current is also changes. Because of change of temperature, meter current is changes. This is called temperature error. Yes, this is called temperature error. Because of change of resistance, meter current is changes, then it is called temperature error. Now to reduce this temperature error, what we are doing? We are adding the swamping resistance. Then how that swamping resistance will reduce temperature? Let us consider. I am explaining the concept with increase of temperature. If temperature is increases, what the meter resistance is also increases, because meter is nothing but a copper. Copper is nothing but a conductor. In all the conductors, positive temperature coefficient, if the temperature is increases, resistance is also increases. But in all the semiconductors, if temperature is increases, resistance will be reduces because of negative temperature. If Rm is increases, then what about the Im reduces? This is called which one? Temperature error. Temperature error. Then to reduce this temperature error, what we are adding? Swamping resistance. Because of swamping resistance, the shunt resistance is increasing. Shunt resistance is increasing. If shunt resistance is increases, what the shunt current reduces? We are not changing any supply voltage. Supply voltage remains constant, means the input current is also constant. Because of this swamping resistance, RSH is increases, ISH is reduces. If ISH is reduces, to satisfy KCL, Im must be increases. Im is increases. Listen please. Let assume that because of temperature error, meter current is reduced to 2 amperes. Reduced by 2 amperes. Actually it is 10 amperes. Now the meter current is 8 amperes. Whenever swamping resistance is connected, again meter current is increased. This 8 amperes again it may be increases to 9.5 amperes. Let assume that. Then we are reducing the temperature. Then before connecting swamping resistance, what is the temperature error? The actual current is 10 amperes. Now it is measuring 8 amperes. That means 2 amperes error. Whenever swamping resistance is connected, again meter current is increases. It not may be exactly 10 amperes. It may be 9.5 amperes, like that. That means we are reducing the swamp. That's why by adding swamping resistance, reduced current is compensated by increased current. Then we can reduce the temperature error. Therefore, due to swamping resistance, due to RSW, reduced current is compensated by increased current. Okay, this is called temperature compensation. This is a theoretical proof. How the temperature error is reduced by connecting the swamping resistance. This is a theoretical proof that you concentrate. Okay. So this about what exactly is swamping resistance. Swamping resistance is also one of the Manganon resistance. It is in the range of 20:1 ratio or 30:1 ratio. The purpose of using the swamping resistance is to reduce the temperature errors. Mainly swamping resistance is used in the ammeters only. No need of any swamping resistance, mainly in the case of voltmeters. The reason I will explain. Then without swamping resistance, this is a shunt resistance. With a swamping resistance, this is a shunt resistance. Okay, clear? Concentrate. Now see, I want to give how to calculate the temperature errors in PMMC meter, that I want to discuss. Even this concept is also applicable for voltmeter. Even voltmeter is also having temperature errors, but don't think like this. No need of any swamping resistance in the voltmeter means that indicate that no temperature. That is meaningless. Voltmeter is also having temperature error, but that temperature errors is controlled itself. How it is without using extra resistance. The series resistance itself will reduce the temperature. That reason I will explain. Then how to calculate temperature errors? Calculation of temperature errors. In two cases I want to explain this. Concentrate. Calculation of temperature errors. This case 1 is if only temperature coefficient of meter is given. If only temperature coefficient of meter is given. Meter is given. If only temperature coefficient of meter is given, then you calculate RMT equal to RM into 1 plus alpha m into delta T. These are due to change of temperature, this is the change of resistance. Then without temperature effect, this is RSH, this is PMMC meter moment, this is meter resistance. Let the meter current is IM. Okay, this is I. This is ISH. Then due to temperature effect, if due to temperature effect on meter, if we consider the temperature effect on meter, there is a change in resistance. We are not considering any change in the shunt resistance in case 1. Let this is PMMC meter moment. Now the resistance changes to RMT. Let if the resistance changes, current is also changes. This is I. Okay, but I remains constant. Then from this, what is IM dash equal to? You tell me. I into, apply the current divider rule. I into RSH by RSH plus RMT. This is IM dash. Okay. Once you know the IM dash, this is change of current. That is actually, if you consider the temperature effect, this is the meter current. This is without any temperature current. This is true value. This is measured value. Then how to calculate percentage error? Percentage temperature error equal to. Tell me. How to calculate percentage temperature error? Therefore, percentage temperature error equal to IM dash minus IM by measured value minus true value by true value into 100. Okay, this is temperature. This IM is given in the problem, that you take IM. Okay, this is case 1. If only temperature coefficient of meter is given. Case 2. Yes. If temperature coefficient of both meter and shunt is given, that means there is a temperature effect on the meter, there is a temperature effect on the shunt also. If the temperature coefficient of both meter and shunt is given, then you calculate RMT equal to RM into 1 plus alpha m into delta T. Similarly, RSHT equal to RM into 1 plus alpha SH into delta T. Okay. Then once you know the RMT and RSHT, let this is without any temperature. This is with temperature effect. Let this is RSHT. This is PMMC meter moment. Then this is RMT. Because of change of current, because of change of both the resistance now, let assume that it is IM double dash. Let this is I. Then what is IM double dash? You tell me. I into opposite resistance, RSHT by RSHT plus RMT. Once you know the IM double dash, then how to calculate percentage temperature error? You tell me. Therefore, percentage temperature error equal to actual value is IM only, or IM double dash minus measured value minus IM by true value is IM into 100. Like this we calculate. Simple calculations. If only temperature coefficient of meter is given, then you can calculate Im dash, then you can get a percentage temperature error. Both are given, you calculate change of resistance due to meter, where alpha m is the temperature coefficient of meter, alpha sh is the temperature coefficient of shunt, then delta T is the change in temperature. According to that, you calculate Im double dash, then you can get percentage temperature error. Okay, this about how to calculate. This concept is also applicable for even for voltmeter also, but in voltmeter there is change of series resistance due to temperature, there is change of meter resistance due to temperature, but here shunt resistance, that is a meter and series resistance, here meter and shunt resistance. Okay, like that we can apply the same calculations. Okay, this about how to calculate temperature errors in the case of ammeters. Okay, but point to remember, note, we know that in PMMC voltmeter, in voltmeter, this is PMMC meter movement na? This is PMMC meter movement, and this is the meter resistance, and this is series resistance. This series resistance is made with which material? Manganese, and it is very high resistance, very high resistance. Understood? That means the manganese resistance is already connected in series with meter. Hence, the series resistance itself acts as a swamping resistance. That's the reason why no need of any external swamping resistance in the case of voltmeter. In voltmeter, series resistance itself acts as a swamping. Therefore, RSC itself acts as swamping. Hence no need of any external swamping resistance, no need of any external swamping resistance. But that is not the case in the case of ammeter. If you take only PMMC ammeter, is there any swamping resistance in series with meter? No. That's the reason why to reduce the temperature error, we can add some extra resistance here. That is a swamping resistance, manganese resistance. No manganese resistance in series with meter here. But in the case of voltmeter, already there is a manganese resistance is there. It is also very high resistance. Series resistance is very high resistance. That take care about temperature errors. Series resistance itself take care about temperature errors. That's the reason why no need of any swamping resistance. Clear? Okay, this about what exactly effect of temperature error in the case of meter, then how to reduce the temperature errors. Clear? Concentrate. Yes, I want to give some special features of PMMC. The special features of PMMC instrument. Note you write. Special features of PMMC. Yes, point to remember, in general, I told already PMMC is used as a voltmeter and ammeter. But this PMMC is also used in ohm meter for detection purpose. Another point, PMMC is also used in rectifier. This PMMC instrument used in, one is rectifier type instruments. In rectifier type instruments also we can use PMMC. Yes, in amplifier type instruments also we can use PMMC. amplifier type instruments. Then it is also used in average responding meters, average responding meters. Then it is also used in peak responding meters, peak responding meters, peak responding meter. Okay. In thermal instruments also we can use PMMC. Thermal instruments also we can use PMMC. Like this, in so many instruments we are using PMMC for detection purpose. Rectifier instrument, directly rectifier will not detect any parameter. Then the output of the rectifier is given to PMMC, then PMMC will detect the parameter. Then amplifier type instrument, directly amplifier will not detect the parameter. Then output of that amplifier is given to PMMC, the deflection of a pointer will give the reading. Okay, like this we can use. But another point to remember, by removing the spring, it is also used as a flux meter. By removing the springs, yes, it is used as a flux meter. It is used as a flux meter. This is one of the special application. Then by using high stiffness spring, it is used as a galvanometer. By using high stiffness spring, yes, high stiffness spring. By using high stiffness spring, it is used as galvanometer. As galvanometer. This is one of the special feature. The another one is PMMC is also used. By using high stiffness spring, it is used as galvanometer. By removing the springs, it is here. These PMMC instruments are used in aircrafts for measurement of voltage and current. Used in aircrafts. Used in aircrafts for measurement of voltage and current. For measurement of voltage and current. This is aircraft supplies. Used in aircraft supply for measurement of voltage and current. Okay. Like this, one of the special feature why it is preferring in aircraft supplies for measurement of voltage and current is it is less affected by external magnetic fields, stray magnetic fields. Okay. That's why if any communication lines will cause us any magnetic field effect, all these interference effect, then that magnetic field is least affected because we are using a large strong magnet in the case of PMMC. That's the reason why this also used in the aircraft supplies. Like this, these are the special features of PMMC instrument. Okay, so many applications are there. But point to remember in detail about this PMMC, I will give in the comparison also. PMMC is more accurate instrument, no doubt at all. In the measurement of DC, it is more accurate instrument. In the measurement of DC, it is more accurate instrument, and it is a high sensitivity instrument. PMMC is high sensitivity instrument. Okay, but the cost of the PMMC is less as compared to EDM, more as compared to MI instrument. As compared to MI type instrument, the cost is more. Okay, that is one drawback. But most of the all are advantages. PMMC is having more advantages. Okay, that's why the only instrument used for mainly for measurement of DC means, even though so many digital meters are there, even though so many electronic instruments also there, but mainly at DC applications, the preferable instrument is PMMC instrument only. With this, according to syllabus for various competitive point of view, the PMMC instrument is completed. Okay, then based on this, I am discussed construction details that is important for theory questions. There is one statement is there, average measuring and average indicating type instrument. Whatever that means PMMC measures DC. Whatever the input we can give to the PMMC, it measures average value. That is one concept. Based on that statement also, you can solve some problems in classroom workbook. Then second concept is torque equation, observation from torque equation. Torque equation is also important, observations also important. Next, extension of range of PMMC instrument as a ammeter. Then as a ammeter, again multi-range ammeters also. RSH equal to RM by M minus 1 formula is important. At the same time, you also concentrate on what is Artan shunt, what is the individual shunt multipliers. The next concept is PMMC as a voltmeter. In PMMC voltmeter, RSC equal to RM into M minus 1, and you also concentrate on multi-range voltmeters. That is nothing but a what is that shunt? Using individual series multipliers, and other one is potential divider arrangement. And you concentrate on how to define the DC sensitivity. DC sensitivity means that is the sensitivity of PMMC voltmeter. Okay. Then how to define the sensitivity. Then next concept is what is the effect of, what is the loading effect due to voltmeter connection. Not only voltmeter, every meter will offer the loading effect. Mainly concentrate on loading effect due to voltmeter connection. Okay. The next concept is what are the properties of shunt resistance, what are the properties of series resistance, what are the material used for to manufacture RSH and RSC. The next one is what is the swamping resistance. The purpose of using swamping resistance is to reduce the temperature errors. Then what is the, how to calculate temperature errors, then what are the special features of PMMC instrument. With this, the theory concept with respect to PMMC is completed. In the next session, we will continue with the classroom workbook questions based on PMMC. This is 4.1. The next 4.2 is MI instruments. Okay. Thank you.